Hello and welcome to another video. In this video we're going to be working on poor pigs. And so I will preface this in saying that this problem isn't going to be like a standard algorithm problem. It's actually more of like a math problem. But let's get into it. So we have buckets of liquid where exactly one of the buckets is poisonous. To figure out which one is poisonous, you feed some number of poor pigs the liquid to see if they will die or not. Unfortunately, you only have minutes to test minutes to determine which bucket is poisonous. You can feed the pigs according to these steps. Choose some live pigs to feed. For each pig, choose which buckets to feed it. The pig will consume all the buckets simultaneously and will take no time. Each pig can feed from any number of buckets, and each bucket can be fed from by any number of pigs. So essentially, when you choose to feed the pigs from buckets simultaneously, you can have one pig feed from multiple buckets, but as soon as you start feeding them, you have to feed them at the same time, and the time to die has to wait until you can feed them again. So essentially, if time to die is like 15 minutes, you can feed a bunch of pigs at 0, and then you have to wait until 15 to feed more pigs. And so wait for time to die minutes, you may not feed any other pigs. And after time to die minutes have passed, any pigs that have been fed the poisonous bucket will die, and all others will survive. Repeat this process until you run out of time. Given buckets, minutes to die, and minutes to test, return the minimum number of pigs needed to figure out which bucket is poisonous within the allotted time. And so let's go through these examples because they will help us with some intuition. So first we have 4 buckets, and we have minutes to die 15 and minutes to test 15. So this essentially means that we only have time to run one test, so we can feed the pigs, and then after 15 minutes, we can see how many pigs are alive, right? If we feed them at 0. So it says the output is 2. We can determine the poisonous of this bucket as follows. At time 0, we feed the first pig, buckets 1 and 2, and feed the second pig, buckets 2 and 3. And then there are 4 outcomes. So if only the first pig dies, then bucket 1 is poisonous. If only the second pig dies, bucket 3 is poisonous. If both pigs die, then bucket 2 must be poisonous. And if neither pig dies, bucket 4 is poisonous. And the second example, also an important one. So we have 4 buckets, minutes to die 15, minutes to test 30. So now we can actually run this experiment twice. We can feed them at 0, wait for 15, and then feed them again at 15. So we can run this twice, and at time 0, we feed the first pig, bucket 1, and feed the second pig, bucket 2. And at time 15, there are 2 possible outcomes. If either pig dies, then the poisonous bucket is the one that was fed. If neither pig dies, then feed the first pig, bucket 3, and the second pig, bucket 4. And then if one of those dies, then you have the answer. So essentially with 4 buckets, you need 2 pigs as well. So what we need to do is we need to figure out the intuition on how to do this. And the way we're going to do this is we're going to start with 1 pig, and then we're going to see what happens when we increase the time. And then we will add pigs and try to figure out like what's the pattern. So let's say we have 1 pig. And the minutes to die, let's call that D, is 15. We'll just use 15. That's pretty straightforward. And then minutes to test is 15. Let's call that T. So how many buckets can we test with 1 pig, pretty much, right? So essentially, the number of tests you can run, let's figure that out first. The number of tests you can run, you need to have a full test, right? So whatever the time to test is, you need to divide that by the time to die. So T over D. You need to floor divide, that integer divide. And then the number of states each pig has is this plus 1. And the reason for this is, let's say we have 15 and 15. So if we can test once, then the pig will either be alive or dead. But, let's actually do this with this, and then we'll kind of see why that is. So here, we can test 2 buckets, right? So if we have 1 pig, we'll have 2 buckets. And the reason we can test 2 buckets is because we can just feed that pig, bucket 1, right? So pig 1 will drink from here. And if it's dead, then this is the poison. And if it's alive, then this is the poison, right? So we can write this down for 1 pig. And for this, we can test 2 buckets. Now, what if we increase our time? And so if time to die is 15, if the time to test is like 25, let's say, then this is going to be the same, right? Because in order to see the result of a test, you need a full time to die minutes to happen, right? So you need 30 minutes to have 2 tests. You need 45 for 3 tests and so on. So now let's change our constraints where we have time to die 15 and time to test 30, and we still have that 1 pig. So now we can run 2 tests, right? We can feed the pig at 0 and at 15, and right at 30, we'll know what happens. So how many buckets can we test here? So we can actually test 4 buckets like so. So we'll have 4 buckets. And what we can do is we can feed. So I'm actually, because we only have 1 pig, I'll just write down what time we test it pretty much. Actually, let me think about this. With 1 pig, how many tests can, no, actually, sorry. So we can't test 4, we can only test 3. Yeah, so we can only test 3 buckets. So the way we would do this is we would, at time 0, we would give pig 1, well, I'm just going to write, so I'm going to replace this with a 0. So at time 0, we gave that pig the bucket. So what we're going to do is we have these 3 buckets at time 0, and we have 30 minutes to test. So at time 0, we will give the pig this bucket here. Then, if it's dead, then we know this bucket has the poison. Then at time 15, we will give this pig, the same pig that we have this bucket. And then if it's dead, then we know that this bucket has the poison. And if it's still alive at 30, then we know this bucket has the poison. We'll do one more just to kind of show this, and then that should be enough to have the pattern. So let's say we have time to die 15 and time is 45. And like I said, anywhere from 30 to 35 and so on, it's going to be the same as 30 because you need enough time to run full tests. So for time equals 45, you can do the same thing, and now we can test 4 buckets. And so the way this would work is we would give the 1 pig this at 0, and if it dies, then this is the poison. We give it here this at 15, this at 30, and if it's still alive, right, we can figure out if it dies at any point, we can say like, okay, here's where it died. So that's the bucket it has to be. Like if it dies at the end, it has to be this bucket. If it dies at 30, it's this bucket. If it dies at 15, it's this bucket. And if it's all the way alive, then it's this bucket. So we can write down a generic case here. For 1 pig, the number of states is time to die, right? Time to die divided by, or it's actually, this is not time to die, this is time to test. Time to test over time to die. So number of time to die over time, or time to test over time to die plus 1. Right? So in this case, we have 45 over 15 plus 1, so that's 4. And for our original case, we would have 1 plus 1, right? Because if you can run 3 tests, and you can test 4 buckets, because essentially you can test the number of tests you can run plus 1, right? So if you can run 1 test, you can test 2 buckets and so on, right? Because if you run 3 tests, you just test it with the first 3, and then if it doesn't die from any of those, it's the last one. So the number of states for a pig, so we'll write that down. Number of states for a pig equals, let's call this time to test over time to die plus 1. That's our formula here. Okay, so now that we know that, let's see what happens if we increase the number of pigs. And the number of states is like how many buckets can we test for a pig with. So let's say we have 2 pigs, and the number of states for each pig is 2, right? Meaning we can run 1 test only, right? So if we can run 1 test, each pig will either be alive or dead at the end. So how many buckets can we test? We can actually test 4 buckets with 2 pigs, and let's show why. So what we can do is, for the first bucket, I'm just going to write down the pig numbers now, and then I'm going to write down, so in this case, we're only going to feed them at 0, so I'm going to have a decimal to represent when we feed them. So like 2.0 means we're going to test pig 2 at time 0. So what we can do is we can test pig 1 at time 0 here, we can test pig 2 at time 0 here, and for this bucket, we'll give it to both of them. So we'll test 1 at time 0 and 2 times 0. And for this one, we're not going to give it to any of them. So there are 4 things that can happen, right? All the pigs are alive. That means this is the poison. Pig 2 dies. So if pig 2 dies, that means this is the poison. Because if it was this one, they both die. Pig 1 dies. This is the poison. And they both die, and this is the poison. So with 2 pigs, with 2 states, we can test 4 buckets. Now we're going to add 1 more pig to kind of make sure we get the pattern. So now we're going to do the same thing, except we'll have 3 pigs. So we'll have 3 pigs with 3 states. With 2 states, actually. Each. Which means we can only run 1 test, right? 2 states means 1 test, as we showed here. Okay. So let's do that. So, and I'm going to write out the buckets because I already did this beforehand, but essentially with 3 pigs with 2 states each, where you can only run 1 test, you can test 8 buckets. And let me show you how that goes. So here we are going to have, so for the first bucket, we'll just feed pig 1 at 0, then pig 2 at 0, then pig 3 at 0. Then we will have pig 1 at 0 and pig 2 at 0. So we'll have a comma. Then we'll have pig 1 at 0 and pig 3 at 0. Then we'll have pig 2 at 0 and pig 3 at 0. And for the last one, we will do all 3 pigs. So pig 1, pig 2, pig 3. And for this one, we'll give it to none. Right? And so notice how all of these are unique. So we can figure out, like, no matter how many pig dies, right? If pig 1 dies, it's this one. If pig 2 dies, it's this one. If pig 3 dies, it's this one. If 1 and 2 die, it's this one. If 1 and 3 die, it's this one. If 2 and 3 die, it's this one. If all of them die, it's this one. And if none of them die, it's this one. So with 3 pigs in 2 states, we have 8 buckets. So you kind of see a pattern, right? With 2 pigs in 2 states, we have 4. With 3 pigs in 2 states, you have 8. And with 1 pig in 2 states, you have 2. So essentially, the pattern is states, right? The number of states for a pig to the power of pigs. And we can even prove this by doing one last thing. So let's take a pig with 3 states. So we did this before, right? A pig with 3 states can test 3 buckets, right? Essentially, we can run 2 tests. So remember, for that one, I think I have it up here, hopefully. Yeah, so right here, right? A pig that we can test twice, we can test at 0 and 15, can test 3 buckets. So a pig with 3 states, now let's actually confirm our formula here by doing 3 states for a pig, and we'll do 2 pigs. And if you do any more than this is going to get like really big. So this should be 3 squared. And let's confirm that. So we'll draw out 9 buckets. 2, 3, 4, 5, 6, 7, 8, 9. So now we have, remember, so for a pig having 3 states, that means we can test it at 0, and we can test it at 15, right? And that's going to be 3 states. So it'll either be dead after the first test, dead after the second test, or alive. That's why 3 states. So number of tests is states minus 1. So let's kind of see how this will work. So essentially what we can do is we can test pig 1 at 0. We can test pig 2 at 0. We can test pig 1 at 0 and pig 2 at 0. And we can also do test pig 1. Oh, now let's actually do, yeah, so we can also test pig 1 at 0 here. Actually, let's do all the 1 pig. Let's do all the 1 pig first. So we can test pig 1 at 15. Then we can test pig 2 at 15, right? So that is 4 buckets that we can test already. And now we basically just have to get every single unique case for the rest of it. So here, we're going to do pig 1 at 0 and pig 2 at 0. Here, we will do pig 1 at 15 and pig 2 at 0. And then we will do, what do we have left? So pig 1 at 0, pig 2 at 15, I believe. And then finally, pig 1 at 15, pig 2 at 15. And for this last one, we're not going to do anything, right? So just to explain again what this means is, so 0 means we will test it at time 0, and 15 we will test it at time 15. So for example, if pig 1 dies at 15, that means we injected it at 0, so it has to be this bucket. If pig 2 dies at 15, then it has to be this bucket. If pig 1 dies at 30, then it has to be this bucket. If pig 2 dies at 30, it has to be this bucket. If both pigs die at 15, it has to be this bucket. If pig 1 dies at 15, or if pig 1 dies at 30 and pig 2 dies at 15, this bucket. If pig 1 dies at 15 and pig 2 dies at 30, this bucket. And then finally, if both pigs die at 30, this bucket. And if no pig dies at all, it's this bucket. So essentially, it's basically like, what are all the combinations of pig and time of injection I can make? And we indeed have 3 squared here, right? So it's the number of pigs to the power, or sorry, it's the number of states to the power of the number of pigs. So now that we proved this to be correct, and you can even try this if you want, you can add another pig or you can add another state, but essentially this will always work. So our formula is the number of states per pig, right? And like I said, the number of tests is the number of states minus 1, because we have to ensure that it passes the whole test. So this is our formula. So now we basically have to figure out, like, okay, well, states to the pigs has to be greater than or equal to the number of buckets we're given. And so states is just time to test over time to die plus 1, right? Lower divide, or floor divide, because you have to have complete tests. So we have the states value, we're given buckets. So now if we have S to the P equals B, and we are solving for P, you could do this two ways. Like, let's say you didn't know the math way of doing this. You can basically just binary search a P until, and you just want to find the smallest value of P that makes it bigger than B. You could do that, but you could also use math here. So basically what you can do here is you can use a natural log. So natural log of this equals natural log of this. And for a natural log, you can move the power out. So you can say P ln of S equals ln of B, and P equals ln of B over ln of S. And so this is the actual formula that we need. So all we need is to calculate S, we're given B, and then we need this. And there is one more thing. So in Python, for example, to do ln, you can actually use math.log. But the problem with this is this is not entirely accurate. With floating point logs, you're going to have some errors. So for example, I think when I tested this with like, I don't remember the numbers, when I tested it with like 125 buckets and 5 states or something, this gave me like 3.000, like 3 or something, right? And the problem with that is you don't want, you want to make sure it's like a whole number, and you want to make sure it's actually accurate. So what you can do is you can just round your answer to like 5 or 6 decimal points, essentially, to get rid of that floating point inaccuracy. But that's pretty much it. And like I said, if you don't want to do this, or you don't want to do the rounding, you could go back up here and just binary search for the smallest value of pigs that makes states to the pigs greater than or equal to buckets. Either one of those is fine. Okay, so now we have enough to code it up. So let's do that. So we're going to have states equals minutes to test over minutes to die, floor divide, plus 1. And then we're going to have our result, and we're going to round our log. And we're going to round our log to get rid of that floating point inaccuracy, otherwise this will fail. So we'll have math.log buckets over, and remember math.log is actually natural log in Python. Math.log states, and we'll round it to like 6 decimal points, and that'll be good enough. So essentially we have some result, right? And let's say this result was like 2.8889. Well, we don't want to have this, right? So if this is how many pigs you need, then you need to take whatever number you have, and you need to round it up to the nearest whole number. So we can just return math, or I guess you don't even need math, right? You just do ceiling of result, because I think math is already imported in here. I don't even think you need log. Let's see. I don't believe you do. We'll find out though. Okay. So there we go, and we have a solution. And so this is all over the place, but this is basically a, pretty much everyone's going to have the same solution. This is basically an O of 1 time, O of 1 space. There's not much to discuss here. Like, you're literally just doing a math operation and not storing anything. And yeah, so definitely kind of a weird one. Definitely like has nothing to do with algorithms, but it's just kind of like a cool math problem. So if you like that kind of stuff, I guess, then, you know, cool. That's why this problem also has, I guess you can tell from if you read the editorial or solutions, or look at the downvotes. Usually problems with like double or triple downvotes, then upvotes have some kind of weird algorithm that's not super related to like coding interviews or something like that. So, but yeah, so hopefully that that explained everything for you. It's definitely kind of confusing for me. I had to actually write out enough of these states and pigs to understand what was going on. But if you did like this video, please like it, and please subscribe to the channel. And I'll see you in the next one. Thanks for watching.